For part 3 of chapter 23, we're going to be looking at transformers, inductors, and RL circuits. So the first question is, what is a transformer? Well, we use transformers all over the place, and you'll see exactly what they do in a moment. But here is a pretty good example of a transformer. You have a voltage that comes in here, and it drives a current that goes around this, that drives the field lines, magnetic field lines you see here. Now, if this voltage is changing in time, that means that the flux is changing in time, and that results in a voltage over here. So if we look at this, on the left hand side we have what's called the primary with NP, which is the number of primary windings. On the right hand side we have what's called the secondary with NS, which is not shown here, NS, and that's the number of secondary windings. Now if you remember from before, the EMF is minus N d phi b dt. So in this transformer, the magnetic field lines are essentially confined to this magnetic material, and our primary voltage is minus the number of primary windings times delta phi b delta t. Since the flux is the same on both sides, i.e. there's no leakage outside of this ferromagnetic material, we've got on the other side for the secondary that the secondary EMF or secondary voltage is minus the number of windings on the secondary times delta phi b delta t. What does that mean? Well, since the flux is the same on both sides, if we write it this way, delta phi b over delta t is minus Vp over Np, which is also minus Vs over Ns. And rearranging a little bit, we get the voltage in the secondary divided by the voltage in the primary is determined by the ratio of the windings between the two. In other words, if you have 240 volts AC over here, we'll say, right, an alternating current, and on this side you want 120 volts AC, all you have to do is make NS divided by NP equal to 1/2, and you've done it. Conversely, if you have 120 volts here, right, at the primary, and you want 240 volts at the secondary, all you have to do is make the ratio of the windings equal to 2. Pretty simple, isn't it? That's what a transformer does. Now, if we look at what this means in terms of conservation of energy, we get another result, because the power on both sides is going to be the same. No power is dissipated in the transformer itself to a great extent. There's a little bit, but for the most part, no power is dissipated in the transformer itself. So the power in the primary equals the power in the secondary. Now the power in the primary is just the current in the primary times voltage on the primary. So that has to equal the power in the secondary, which is just the current in the secondary times the voltage in the secondary. If we rearrange those, we get Vs over Vp equals Ip over Is. You'll notice that, right, the symbols are swapped. They're inversely related. So when we take this and we step from 240 volts down to 120 volts, the current doubles. All right, the current doubles, and it doubles because this equation holds. Now, when it comes to realistic use of transformers, one of the things you'll find all the time is out at the street, you've got, well, this will be an exaggeration, but you've got, say, 14,000 volts, and you have a transformer that brings things at your house down to 240 volts. Why do we do that? We do that specifically because it cuts down on the current over on that side, right? The 14 kilovolt side carries very little current. since power dissipation in the line, right? Power dissipation in the line goes as I squared R, and since we can't get rid of the resistance of the line, if we minimize I squared, we cut down on the amount of energy that gets lost in the transmission lines carrying power to your house. Another thing that's important here is that not any form of primary voltage will work. So if you stuck something like a square wave in, then on the secondary you would only see these little spikes, right, whenever the voltage changed on the primary. Because once you have a DC voltage, everything settles down to everything settles down, and there's no change in the flux. So you really only get the edge effects, right? So the ideal waveform to drive a transformer with is in fact a sinusoid. If you drive it with a sinusoid out of the other side, you get a sinusoid. There are several safety issues associated with electrical appliances, in addition to not going out and grabbing the 14 kilovolt line outside your house. So where are these safety issues, and what do they mean? One potential issue is that the the convention is black is hot, white is neutral, and green is ground. And by neutral we mean it goes back to the neutral or grounded side of your power supply. By grounded we mean it goes to the actual ground. If you were to get out and look around your house over by the meter, you'll find that there is a metal bar or metal pipe driven into the ground and a fairly large cable that connects that into your house. So the ground wire on everything in your house should in principle connect to the ground outside your house. The earth essentially acts as a huge, enormous electron dump. We can stick as many electrons into the earth as we want, and it makes very little difference. So potential safety issues. If the black wire somehow gets shorted out against the casing, okay, that's a potential issue. You know, that means your casing is at whatever your line voltage is. And if you touch your casing and you're grounded, you give current a path to ground through you. Another potential issue is there could be a little bit of leakage current through some resistive contact with the casing of your appliance. And by appliance I mean your stereo system, your Xbox, your computer, your refrigerator, your microwave. That's what I mean by appliance. So there could be some leakage resistance there. So you had some voltage on the exterior of the appliance, and again, current then has a path to ground through you if you are grounded. Final way that things can go wrong is if the ground is broken. If the ground wire is broken, like down here, that means you can induce an EMF on the casing, right? Because flux, right? You know, your microwave has a cyclotron in it. Your stove runs fairly high currents, unless it's gas. Your radio or your stereo has some fairly high power electronics in it, so you could induce an EMF on the casing, and again you get a path to ground through you. Now, what are some of the ways we deal with this? One is we typically have in the circuit a circuit breaker, and a circuit breaker measures the total amount of current flowing to make sure it stays below some threshold. Usually you'll see on your circuit breakers that's 10 amps or 15 amps. You may have some that are 20 amps, right? And when you get into industrial usages, you'll find 30 amps. You'll also find in the main breakers of your house, sometimes 50 amp branches that don't go to any particular appliance, or maybe a 50 amp that goes to your stove, depending on what kind of stove you have, or to your air conditioning system, or to your water heater, right? Some 50 amp appliances. So one of the things we have in place for safety measures is that breaker. Now, on a lot of equipment, instead of a breaker, we use a fuse. And a fuse, you'll see them all the time. They'll have a couple of metal ends. There'll be a glass case, right? And if you look inside, there's a little piece of wire. Well, that wire is designed so that when you hit the current limit, which is typically for most fuses like 10 amps or 15 amps, when you hit the current limit, that wire actually burns out, right? And it breaks the circuit. You'll see them in your car. There'll be a little plastic package like this, be a metal tongue coming out like that, and then there'll be a little wire you can see here. They always make the wire that's the fuse part visible so that you know when it's burned out. And again, here, when you flow too much current, that element physically evaporates. Another way, and a safety feature you should use around sinks and in bathrooms, around showers, anywhere there's water, is what's called a ground fault interrupter. So a ground fault interrupter isn't concerned with what is the total current flowing. So when you have current flowing through an appliance, there's the hot line coming in and the neutral line going back, and the total current flowing through a surface that these two pass through should be zero, right? So you have the same amount of current going out as you have coming back. Well, what a ground fault interrupter does is it measures the difference. And when the difference is not zero, it cuts the circuit off. So these are especially useful around water, because water is one of those places where very often you'll end up providing an alternative path to ground that doesn't draw enough current to cause the main circuit breaker to drop or to trip, but there is enough difference between the two circuits for the GFI to recognize that something is wrong and interrupt the circuit. Another safety issues. Many of you probably live in older homes. You've probably considered at some point getting one of these 3-prong, right, to 2-prong adapters, because you have either you have a plug somewhere in your house that doesn't have the 3rd prong. And remember, the 3rd prong is ground, right? The 3rd prong, I can't write it all today. The 3rd prong is ground. If that were spelled G-R-O-U-N-D instead of the Egyptian hieroglyphics it looks like. So the 3rd prong is ground. Now, why are these allowed at all, you ask? Because they keep you from grounding your appliance, which means you're now grounded through the neutral, right? You're grounded through the neutral all the way back to wherever your power supply is. But your power supply is not necessarily anywhere nearby, which means this, if you don't have a local ground, this neutral can drift from local ground, and you, being attached to local ground, have to worry about that. So how do you actually deal with this? If you'll notice, these have a little tab right there. Alright? And that little tab, when you look at an outlet in your house that only has 2 prongs, there's usually a screw right in the middle. Now, if this outlet was constructed properly, that screw connects to ground. So, if you are not taking the screw out and putting it in and screwing this in place, then you are not grounding your appliances, probably because the screw has been painted over, right? and even though you're touching it, you're touching the paint, you're not touching the actual screw. So you have to take the screw out, you have to plug this in, you have to put the screw back so that it goes through here and provides ground, local ground for your appliances. Please do this. I once cautioned a chemistry professor about this because he had he did not have a 3-prong available for his computer. He used one of these to plug his computer in, and I said, well, the problem with that is because you're not grounded locally, you can actually build up a charge on your computer. And that turned out to be a little prophetic because 5, 10, 15 minutes later, something like that, and this was years ago, this wasn't here at Delta State, but 5, 10, 15 minutes later, he was yelling ow because he had actually gotten a significant shock off of his computer, which had in fact built up a pretty good charge. So now we want to move on to something called inductance. Now, one of the first things that it discovered was mutual inductance. Mutual inductance is actually how we broadcast and receive FM radio. So mutual inductance plays a big part in your life if you still listen to FM radio. But when it was first discovered, you take a coil like this one on the left, sorry. Whoop, that's not what I meant to do. You take a coil like this one on the left and you run a sinusoidal current through it, or a changing current through it. Well, that's generating a magnetic field. That magnetic field penetrates through the coil on the right, and because d phi dt generates an EMF, right, you get an induced EMF on the coil on the right. Well, the relationship they discovered was that EMF, right? That EMF is minus a constant, which they called mutual inductance, times delta I1 delta T. So the EMF over here depends on the current over here. Well, what was really cool was when they ran it backwards. All right, when they ran it backwards and they put the voltage over here, right, and got a current over here, current I2 over here, they found out that it induced a voltage here and that the same constant was there, right? So that constant apparently depended on the mutual geometry of the two coils. We call that the mutual inductance, and it has units of volt seconds divided by amps. So a volt divided by an amp is just an ohm, has units of ohm seconds. We call an ohm second a Henry. There's another term or another issue around inductance, and we sort of spoke to it with the back EMF from a motor. So there's something called self-inductance, and it has a similar form, which is the EMF across a coil is minus the inductance times delta I delta T. We call devices that have significant self-inductance inductors. If we compare this to the EMF is minus N delta phi B delta T, we conclude that the inductance is just L, all right? L equals N delta phi B over delta I. For a solenoid, where B equals mu naught Ni over L, the flux is B times A, so delta phi B would be mu naught Na over L times delta I, and that gives us delta phi B over delta I, right? Going back a slide, delta phi B over delta I times N is the inductance, so the inductance is mu naught N squared A over L. The inductance depends completely on the geometry. the energy stored in an inductor is 1/2 Li squared. Now if you remember back when we looked at capacitors, the energy stored in capacitor is 1/2 CV squared. Long and short of this is capacitors store energy in the electric field, which is given by their relationship to voltage, and inductors store energy in the magnetic field, which is given by its relationship to the current. So basically, to kind of repeat that, the relationship between capacitors and voltage is the same as the relationship between inductors and current. If we look at an RL circuit, if remember we had an RC circuit we looked at before, it's very similar to this where we just had a capacitor here instead of an inductor. Well, if we look at an RL circuit, we get a current behavior that looks like this curve, this exponential curve, right? And then this exponential decay when we turn it off. Well, as with the RC circuit, when we engage the battery at a time t equal to 0, what we get is the exponential, right? Exponential increase in current. I equals I naught 1 minus e to the minus t over tau. Tau in this case is L over R. Remember for RC circuits, tau was RC. So tau is L over R for this circuit, and I naught is just V over R, where this voltage supply is giving us V volts. So I naught is V over R. When we disengage, right, we get the decaying current, I equals I naught e to the minus t over tau. And remember, tau is still, for this, tau is still L over R, right? Tau is L over R. All right, that brings to an end segment 3 of chapter 23 in RL circuits. I'll be providing some problems related to this, as well as other problems, and I look forward to finally catching back up with you guys. All right, have a great spring break.